Okay, so you've definitely seen this formula before. You probably used it back in science class. But that simple little equation we all had to memorize? Well, it has a surprisingly messy and honestly a pretty fascinating story behind it. So, let's dive in.
And there it is. Voltage equals current times resistance. V equals I times R. It's just so clean, so simple, and it feels perfect. This equation is the absolute bedrock of modern electronics. It's the first thing you learn, and it's the principle that makes literally every single electronic device you own possible. It feels so absolute, doesn't it?
But what if I told you that this elegant formula didn't just pop into existence out of thin air? That it wasn't some single flash of genius? The real story here is actually a story of struggle, of changing ideas, and of the messy, brilliant, and very human process of scientific discovery. So, to really understand the law, you've got to understand the man first. And the reality of his work was, well, anything but a straight line.
This is George Simon Ohm, and back in the 1820s, he was not the legend he is today. He was just an experimenter, working with the tools he had at the time, and those tools were notoriously flaky and inconsistent. I mean, can you imagine trying to discover a fundamental law of the universe when your power source keeps fluctuating all over the place? That was his everyday reality. In fact, Ohm's own understanding of his now famous law changed dramatically over just a few years. His whole journey is this perfect example of how the actual instruments a scientist uses can completely shape their thinking. You can actually see his work happen in three distinct phases. First, in 1825, he's using this unstable power source called a voltaic pile, and he's describing what he sees as a loss of force in the circuit. But then he gets a better tool, a more stable thermocouple, and suddenly his language shifts. Now he's talking about an exciting force. The improved tool gave him a totally new perspective. And finally, by 1827, he kind of sets the physical experiments aside and just attacks the problem with pure math, refining his idea into what he called electroscopic force, which was his term for what we now call voltage. The tools changed, the language changed, and the idea itself just kept evolving. This whole process finally came together in his 1827 paper. This was the moment that all of those messy experiments, the changing words, and the trial and error thinking were finally boiled down into the elegant mathematical law that we all know today. So, now that we kind of appreciate the journey it took to get here, let's break down the language Ohm gave us. What exactly are voltage, current, and resistance? Let's start with voltage. You'll see it written as a V or sometimes an E. The easiest way to think about it is like water pressure in a pipe. It's the push, right? It's the potential energy just sitting there, waiting between 2 points, ready to make things move. If you don't have any pressure, you're not going to get any flow.
Okay, next up is current, shown with an I. Now, if voltage is the pressure, current is the actual flow of the water itself. It's the measurement of how much electric charge is actually moving past a point over a certain amount of time. It's the go. And finally, that brings us to resistance. This is exactly what it sounds like. It's the opposition to that flow. In our water analogy, resistance is like making the pipe narrower. A really wide pipe has low resistance, so tons of water can flow through. A tiny, narrow pipe has high resistance, and it really restricts that flow. The key thing to get is that these three ideas are always connected in this special relationship. Understanding the terms is one thing, but the real power of Ohm's law is actually using it as a tool. So let's see how this thing gets put into practice. And there's a fantastic little trick for this, the Ohm's law triangle. It's so simple. You just cover up the thing you're trying to find, and the triangle tells you exactly what to do. Want to find voltage? E. Cover it up, and you're left with I times R. Need to find the current? I. Cover it, and you get E divided by R. It's just a brilliant, simple way to keep the relationship straight in your head. And this is where it becomes so practical. Imagine you're building a circuit. You know you have a 9-volt battery, and you know the resistance of the parts you're using. But how much current is actually going to be flowing through it? Well, you don't have to guess. Ohm's law, I equals V divided by R, gives you the exact answer. This is absolutely fundamental for designing electronics that actually work the way they're supposed to and, don't catch on fire. Of course, most circuits aren't that simple. They rarely have just one resistor. When you line them up one after another or in series, the current has to push through every single one. So you just add their resistances together. Simple enough. But when you arrange them in parallel branches, it's like opening up more lanes on the highway. The current has multiple paths it can take, which actually lowers the total resistance. The math is a little different, but the principle is the same.
Understanding this is absolutely key to figuring out more complex circuits.
So why does a discovery from almost 200 years ago still matter so much? Because the world you're living in right now is quite literally built on it. I mean, every single one of these things relies on the principles that Ohm figured out all that time ago. Engineers are using his law to control the electricity in your phone's processor, to design the circuit that safely charges your laptop, to create the perfect amount of resistance in your toaster's heating element to make great toast instead of a fire. It's not an exaggeration to say it is everywhere. And that kind of brings us to a final thought here. Ohm's story is this powerful reminder that science isn't just a book of perfect, unchanging facts. It's a human process, a process of refinement, where our ideas evolve right alongside our tools and our understanding. And it really makes you wonder, doesn't it? What accepted scientific law of our own time is maybe just in phase 2 of its own messy, brilliant discovery? Something to think about. Thanks for watching.